Praveen and Nils, would you please start your presentation, and welcome to Nullcon Online.
Hi, I guess you
Yes,
can see my screen.
absolutely. We can see your screen, Praveen.
Great. So I'm Praveen. This is a joint talk with Nils. We both are senior security analysts at RISC here. This talk is going to be how to, based on fault injection, and we achieved arbitrary code execution on RISC-V based RISC-V based devices using fault injection, and we'll show you how we achieved this. So we start with a basic introduction to fault injection attacks. Then we explain what is our exact contribution and show different approaches to controlling program counter on RISC-V based devices. And we finally show experimental results on one of the RISC-V based SoCs. So what do we mean by fault? A fault is anything that triggers an unexpected and incorrect execution, but that happens by intentionally altering the environment. So sometimes faults can happen unintentionally, but here the goal is to actually alter the environment in such a way that the program execution changes. Let's take an example. So this is a simple piece of code which checks signature of an image to authenticate before it executes it. So you can see there is a function called check signature, and the image is provided in this argument. And if everything went well, the authenticated will be set to true. And if that is the case, then the device starts executing the image. Otherwise, it just resets the device, or it knows that the image is not a proper one, so it should not continue execution. So this is normal, what you see in most of the secure devices. So let's say we want to induce faults while this piece of code is being executed, right? So specifically, we want to induce fault when this if check is being performed. So as I mentioned, if this authenticator is true, then it should go here. But let's say I induce a fault when this if check is happening and then change the outcome of this if condition. What can happen? Instead of going to the else, the program actually starts executing, and thereby an image which was not authenticated will be executed on the device, giving attacker runtime control. So that's what fault injection can do. But how can we trigger faults into devices? Typically, any integrated circuit has a safe operating area where what kind of frequency it can operate at, what kind of voltage levels it can operate at. So you see here the safe operating area, right? Yeah. So this is the safe operating area, and then anything beyond this is not gonna make the chip work. But let's say the operating area is 1.8 to 5.5 volts. And if you go beyond 5.5 for a long time, that could kill the chip. right? So it's overpowers and then it might kill it. Then if we go below 1.8 for a long time, the chip might not even boot, so nothing happens. Both those scenarios are not something we are interested in. What we are interested in is making changing this voltage for a very slight amount of time so that the chip doesn't die or chip doesn't just not boot, but it keeps operating, but it triggers a faulty execution on the program. So we want to change this voltage outside the safe operating area only for a very slight amount of time. And then if you remember the previous example, what we want to do is we want to change this voltage exactly when this if check is being executed. And by that, we would be able to execute an image which was not authenticated. Then there are a lot of techniques with which we can inject faults into devices. We can use laser. This allows us inducing very precise faults into a particular part of the chip, even like your CPU or memories, flash. So you can very precisely inject faults into a particular component, even to the level of a few registers. As I already mentioned earlier, you can use voltage to either go beyond the operating area or below it. Electromagnetic pulses to create EM faults. Temperature, change the go beyond the operating conditions of the chip, or even clock frequency. So there exists a lot of ways in which you can induce faults into the device. But another thing to note here is that faults are not limited to just hardware. You can induce faults even just from software. There are quite some results in the recent past which proves that. For example, row hammer attacks, which attacks the DRAM by repeatedly accessing certain memory locations. Then we have clock skew, where this is pretty much similar to what I explained before, the physical faults, but you don't really have to change anything on the device. You just need to write a program in the non-trusted part of the system, which can change either the clock frequency or the voltage that the device operates on, and then that can manifest the required faults. There are some more results that are similar to that as well. So faults are not only just limited to hardware, but you can also induce them with software as well. And so there are a lot of results using fault injection. Lately, it has been quite, let's say, in the news. You can see some of our colleagues also had results on, for example, ESP32 secure boot. So we were able to bypass the secure boot using fault injection, and then Ninjato hacking, all sorts of things that were done with FI. So on this particular topic that we are going to present today, a lot of our ex-colleagues and ex-interns also worked on it, similar thing. Some of the examples that you can see here specifically controlling PC on ARM. This was one of the first papers which shows how fault injection can be used to directly control a program counter. And if you can control program counter, then you can execute your own code on the device. So, but this one was particularly for ARM 32-bit architectures. So then there was later another presentation by Nick and Cristoforo. This relates to a bit more generic way of inducing faults on data transfers so that you get code execution. So not only just changing the program counter, but there are other options that they show are possible to achieve the same end result. So in this, our contribution here is that we do a similar thing, which is showing that program counter can also be controlled on RISC-V based devices. And while doing that, what we discovered is that we will get into a bit more details later, but the idea is that in RISC-V ISA, program counter is not directly accessible to the programmer. So it's internal, it's not directly exposed in the programmer model of the ISA. So the previous attacks, basically, for example, on ARM, how they work is you have, you change the destination register of an instruction to program counter. And then if you can do that, then you can control PC, right? But this is possible on ARM because ARM exposes the PC directly to a programmer. But in case of RISC-V, PC is not directly exposed, right? So then our expectation before we did this experiment was that, yeah, we cannot directly control PC, so we need to find indirect ways. But during this experiments, we realized that we were still able to directly change PC. We do not exactly for 100% know how this happened, because sometimes fault injection is like that. We don't know what exactly happened, but we have some hypothesis. Nils will explain later during the experimental results what I'm talking about here. But yeah, so that's also another contribution, which is that we find new fault models, not just the direct instruction or data related, but more related to the hardware itself. Yeah, so then as I mentioned, we are doing it on RISC-V based devices. So some of you may already know, but for those who don't, it's in free and open instruction set architecture. And the good thing here is that there is no license fee to use it. And yeah, that makes brings the barrier down. And it's based on reduced instruction set computer principles, just like ARM or MIPS. And it has modular design, right? So there is a base integer ISA that is there for all the implementations, but then it can be easily extended. And because of its modular nature, it makes it very easy to extend it for your own use case. And we expect that RISC-V will be very popular in the near future because of the reasons that I just mentioned. So let's see a bit more into the details of the RISC-V. And if you look at the registers available, there are 32 registers. Yeah, I mean, if you looked at any of ISAs, you know there are a bunch of registers. Some of them you could already see. For example, return address, which is called link register in ARM, and then you have the stack pointer, and then you see some temp registers that are typically used, to transfer data during the program execution from one to the other or operate on the data. And then, so some registers to store the function arguments, return values, and so on. So these are all nothing fancy here. So if you looked at any other ISA, you would see very similar things. But two things here, as I mentioned already, you don't see a program counter here. So this is not exposed to in the programmer model. And that's why we do an indirect way, right? So we still want to get code execution, but we can't really control PC. At least, as I mentioned, that's our understanding at the beginning. So what we wanted to do was we wanted to do indirectly change the program counter. That we could do, like for example, when a function is exiting, then it has to go back to the called function, right? Which is the caller, and the address at which it should go back to is typically stored in this return address register. And we could change this register and start executing our payload instead of the previous function. So that's one target we wanted to have. And the second one is stack pointer. So again, here you have when there are nested function calls or the local data, you have all of them allocated on the stack. If you can change the register where the top of the stack is located, we can redirect the program execution, change the data, and that all could lead to getting code execution on the device. That's about registers. Let's look at some of the details about instructions provided. So as you can see, there are 6 different instruction formats, right? So each instruction will be coded using 32 bits. And instruction is a combination of what is the operation that it needs to perform, what is the source register, and what is the destination register. So as you can see, different instructions have different way of presenting that information, but overall, what is the instruction can be decoded from 3 different parameters here: func7, func3, and opcode. Okay, so these 3 combined will tell you what exactly it needs to execute, and then RS1 and RS2 are source registers, and RD is the destination register. So based on the instruction type, some of them might be present, some of them not, but you at least have 1 opcode, 1 source register, and 1 destination register, right? Sorry, 1 opcode and either 1 source or 1 destination register. Okay. So if you go a bit more into detail, this is how different instructions look. You have the opcode here, and then other parameters that I just described. But in particular, what we are interested in is load operations. I explain why a bit later, but let's say the load word instruction here. So there is an opcode here. This I believe is font 3. So these two combined will tell that it is a load word operation. And then you have RS1, which is a source register. And this is immediate value, which means where from RS1, you add what is there in the immediate to go to that particular location, and RD is going to be the destination register. So basically what it does is it loads from the address that's specified by RS1 and immediate to register RD. So it's just basically loading a word from the memory. Why are we interested in load operations? Because firstly, they are operating on attacker controlled data, right? So we as an attacker can specify what is being loaded. Even if you remember the first example that I was mentioning, the image which is being authenticated is a collection of data that we are providing to the device so that it can authenticate the data that we are providing. So we have control over what goes in here, and typically they are executed multiple times, right? So basically loading from memory, external memory to, for example, internal memory, there will be a bunch of load operations, loads and stores. So that means these are executed a number of times during the copy. Of course, there are other ways. For example, if you use DMA, this is different, but in most of the cases earlier during your, for example, secure boot flow, you may not use DMA, you just do a simple copy. And most importantly, they are not protected, especially against fault injection, because yeah, I mean, you don't trust the data, right? Anyway, you are going to authenticate and do proper authentication before you execute it. So you don't really have to add any protection. And I mean, that's the normal thinking of the designers. And yeah, as I also mentioned, there's the use case. So this secure boot, in case of secure boot, you load the data from an external flash, for example, into internal RAM. And this involves a lot of loads and stores. Yeah, so that is why we are interested in injecting fault into load operations. And finally, we say that we are targeting LW, which is load word, but you can do the same attack on other kinds of loads as well. So there is nothing stopping us from attacking other load operations. Okay. Now, how we actually do this, right? Let's go back and see. I mentioned two registers, right? The link register and the stack pointer register. So the idea here is that we change the target register in an operation, in a load operation, from something which is normally used by the program to our interest register, which is RA here. So if you take any disassembly of a simple memcopy operation, you would see a bunch of loads happening from the memory into the register. So this is a temp register T0, and this is actually loading from the memory address stored in T4 into T0, right? So this is simple load. Now the idea is that we want to change this T0 to RA. So how can we do that? So if you look at here on the right, you see how this particular instruction is encoded in binary, right? So this 32-bit instruction refers to this one. Now, if we just change this particular one here to 0, then this instruction will completely change. So instead of the data being loaded into T0, it will be loaded into RA. And now imagine if at this location, we store our payload address, right? Then because of our fault, the RA will have our payload address instead of the previous function's return address. Now, if you do that, what happens? When the current operation, which is in this case memcopy, is returning from the copy operation, it will start executing what is there in RA, which as we have loaded with our value, then the device starts executing our code. So that's the way how we take control. Yeah, so another example, let's say instead of T0, it's T2. Then this is how the binary looks like. And here, instead of 1-bit modification, we need to modify 2 bits using fault injection. Then we get the same result again. Okay, so that's what we want to achieve. So we discussed what is fault, how to induce faults, what is RISC-V ISA, what are the registers, what are the instructions, and then finally we discussed how we can induce faults so that what we want to do, for example, RA corruption can be achieved. And similar way we can also do with stack pointer as well. Now, finally, what we have seen all the theory. Now we want to see how to perform this attack. And before we describe the actual attack itself, the target. So this is, as you can see, a microcontroller from Sci-Fi. It's based on RISC-V, and we specifically used a Hi-5 REV development board. And then, yeah, it has the RISC-V base integer instruction set implemented, and it can run quite a reasonable speed with 320 plus megahertz. For inducing voltage Fi specifically, because this is what we did, we need to look at 3 different parameters, right? The first one is the glitch delay. So here is the place where you have your trigger. Let's say this. Let's go back to the previous example. This is where your if comparison is happening, but you don't know where exactly this if is happening in your program, right? Like it's not straightforward to know where exactly it is because of several reasons. Now you want to have a proper point in the program where you know, okay, this is where I know in the program where exactly I am, right? So this is the place. This could be a UART output. This could be a flash read. You know, this happens all the time at the very precise moment. So from here, you need to go to the actual if check. And this is what we call the glitch delay. So this glitch delay is from the reliable trigger to the actual operation of interest. And then you need to change the voltage, right? You need to take it to take it away from its operating voltage, either by reducing or increasing. Typically, we go below because that is safer. And finally, how long you want to induce this glitch, so how long you want to keep the voltage to that level. So these three are important parameters. And sometimes you may also have to, not sometimes, but most of the times you need to provide your own power supply so that you can control it. And sometimes you may have to remove the capacitor so that your glitch is a lot more effective. So this is a typical setup looks like. We have the glitch generator to generate the voltage glitches, and glitch amplifier, which amplifies the given voltage glitch, which will be provided to the chip or the target in this experiment. And then from the target, you have a trigger signal. Remember, the trigger signal is something that comes here. And then you need to communicate with the glitch generator and the target using a PC. And then, sometimes it may also be good to have a way to reset the device directly during fault injection. So this is how it looks like. You can see the spider, which is a glitch generator, glitch amplifier, and then the bunch of pins here, which can be connected to control either the triggers or resets. And this is the, if you zoom in here, this is what is actually connected to the power line and provide voltage directly by ourselves. And then we have a program to control all the setup, when to inject glitches, how to inject glitches, and when to get the data, and then the parameters that we need to give, and finally, once we have the data, how to interpret it. So let's take a simple example here. This is before we do the actual test, we want to know the parameters that I just described, how they look like, what are the ideal parameters. So to do that, we do a simple test like doing 10,000 times a simple add operation and see if we get output, proper output or not. And during this add operations, we just glitch. And then you see here the output from the function. If the output is 10,000 as expected, then it will be marked as green here. If the device resets or doesn't respond back because of our glitch or fault, because we mark it with yellow, and reds are something that are interesting because they provide an unexpected output. For example, instead of 10,000, it sends back 9,999, or something like that. So the reds are our interesting results. And specifically here, we are interested around this region because here we see a lot of reds, and for the actual experiment, which involves corrupting RA or SP, we use this area. So this is how we do characterization. Now I will give it to Niels to present the actual experimental results for RA or XP.
Thank you.
I
think you can hear me now.
Yes.
And I think you can see it now. All right. Yeah, one thing to note here is that if you are attacking a real device, or you were trying to do something actual, like some actual attack, you would stay a bit longer in this phase and try to optimize where you get these successful results. But because we're so abundant in this particular CPU, and we want to generate these nice pictures for our own experiments as well, we picked the area where we covered both successful and non-successful faults. So once we had this, we had our our settings for our fault injection campaign. So then the second thing we needed was a experimental setup in terms of software, which we can use to show that the attack we proposed is actually possible. So for that, we used a small software that's very similar to what I show you here on the screen. So there is a test function, which is the entry point for the experiment. We wait to receive a command from outside to actually start the experiment. And then we have a sort of mem copy, but slightly modified so that it works for our setup. So what we do is we put some local memory address in S7. So that would be our pointer in a real mem copy to the source of the mem copy. And then we set up, we load the address of the source of the mem copy into another register, and we store that in this previously used memory address. And we need to do it like this because in a real mem copy, you also have this method where you dereference a pointer. And that's what you see here in this load word operation. So here you dereference the address of S7, which is this local memory address, which contains our payload destination. And since we are doing an experiment here, we put everything just in our local memory already. So in a real world, this payload would be somewhere in your external flash, for example. But here we just put it alongside in a memory. And what the payload does is it does two things. It puts the current return address into temporary register 1 and a magic value in temporary register 2. And this information helps us identify if our experiment succeeded in executing this payload. Because if in a normal flow where there are no faults, we start executing the test function, we receive a command, we receive the command to actually start the mem copy, we do the mem copy, and then we reach this return function. And what the return function does is it sets the program counter to the current return address value. If there was nothing weird going on, the return address contains this location, the next instruction after our jump. And then it just keeps in this loop forever. Now, if we take our fault and our fault is successful in changing this temporary register into the return address, then after we call the return function, the program counter is set to that value in the return address, which is our payload destination. So and then after each, it's not shown here, but after each attempt, we dump all the register values. And if this T2 register contains the magic value that we put here in our payload destination, then we know that our attack succeeded. Here I just showed one instruction, but in reality, there will be many instructions in one loop iteration. If you would compile an actual mem copy, it would stick to those temporary registers. There are 6 or 7 or 8 of them. But since we are doing experiments here, we also try to see what happens if we just use all the registers. And our expectation was that there is a higher success rate if you use all the registers, as you cover more of those temporary encodings. And yeah, how this would look more or less in memory is that on the one hand, you would have this code that you trust, which is executing the mem copy. and it will copy into memory this untrusted code, untrusted data, which first contains the payload and then the address of that payload many times, so that every time you copy this address of the payload is a potential successful fault could happen. And we need that level of indirection, like Praveen said, because we are not loading this address into the program counter directly, but we are dereferencing it into another register. So in summary, since we are doing experiments with a target we completely control, we can cheat a little bit by using a GPIO pin to trigger the fault, to have a very constant moment in time. In a real world scenario, you might not have this, so then you might have to rely on using USB activity or UART activity, or if nothing is there, you might have to take some kind of side channel analysis probe, like to measure current or to measure EM fields to get a reliable point to trigger your fault. We considered our experiment successful if we observed this magic value in T2. And we did 2 rounds of experiments, one where we use almost all of the registers that are available to us in our memcopy, and another one where we only use the temporary registers. And what we found is that both gave us successful faults. Yeah, this is a picture that Praveen showed you also during the characterization step. So there's the green, which had no effect, and then you can see that there's this curve of yellow where stuff started happening. And if you're not colorblind, you can see there are some red dots in here as well. Those were the successful faults. Yeah, this is it in numbers. So you see the amount of attempts we did, and a very small percentage of them succeeded. Note that this is a very small, one of the reasons this is a small percentage is because we had a wide range of parameters we tested. If you were to zoom in into a region or a configuration of parameters where you observe more red than others, for example, here you see none, this would increase your success rate, which is something you would do in a real attack. But since we're just doing experiments here, we stick to those. And also it allowed us to better compare these different scenarios. Yeah, what we see here is that when we only use the temporary registers, the success rate drops by half, or even more, almost by a factor of 10. And then in this last column, I gave you an indication of the time until we had our first successful glitch. And this is, of course, a number with very high variance because, yeah, since it's a statistical exercise, so you might get lucky, you might not get lucky. But yeah, you can see this big order of difference between the two. Now I will try to one last thing I would like to share with you is that we observed something interesting here, because if you recall what I showed you before, the payload, what it does is it sets a temporary register to the current return address value and another one to the magic value. But one thing we also observed is that we ended up in our payload, so we got this magic value, but the test function was the return, well, not actually the test function, but this jump to test function was the value in the return address. And this suggests that we somehow managed to reach our payload without hitting a copy instruction such a way that the address gets loaded into RA. And yeah, if we split those out from the successful results, you can see that in both cases, it's more or less a 50-50 division between reaching our payload through the return address, and also and the other half was able to reach the payload without changing the return address. Now, there are some theories on what happened here. Perhaps we changed the load word into the jump and link register instruction, which takes a value in a register and jumps to it. So you don't control PC directly, but it's almost directly because you change the PC to a value in a register that you specify. However, another thing this instruction does is it sets a second register argument to the basically the return address program counter +4, but it doesn't have to be the return address register. However, when we looked at the other registers, we did not observe this value. So it could happen, but it's not likely. Another thing that could have happened is that we are executing our load words in a loop, and this loop goes back to the beginning of the loop using a branch instruction. And this branch instruction takes an offset, and perhaps this offset was changed. Again, this could have happened, but it's also unlikely because it would require very specific bit flips to get the exact offset required. And then another possible explanation is that even though we cannot directly load values into the program counter using the available instructions, if you think about the hardware, in the end, the CPU will have one big multiplexer to select which register to use for a value that's somewhere else in the CPU. And even though it's not exposed, this multiplexer will also be able to reach the program counter register because it needs to update the program counter. So although it's not exposed as an instruction, there is still a data path from whatever value you have in your CPU for the current operation to the program counter. And what we suspect, and if you would look at open source implementations of the RISC-V architecture, you can actually see that this data path exists. So this is our what we think is the most probable hypothesis about how we are able to reach our payload without going through the return address indirection that we expected to be necessary when we started these experiments. So we are running a bit out of time, so I'm gonna just fly through this second set of experiments. Just in a brief summary, we also did the same experiment, but we tried to target the stack pointer. One downside of using return address as a target is that if you are not in a leave function, so memcopy usually is a leave function, which means it doesn't call other functions. So it does not override the return address. But if memcopy would call more functions, then the return address value would be updated to the return address of that calling function, and that would negate your attack. However, if you do it through a stack pointer, then you would need another level of indirection because you have to go not only through the return address, but through the return address stored on the stack. But this is more powerful because you are not restricted to those leave functions. And then it's basically a classical Stack Overflow attack you know from software exploitation. But we just triggered it not through a stack buffer overflow, but through fault injection. Yeah, we also succeeded in this. If you compare those percentages, they are lower. And one number that really stands out is this 8 minutes here, because here we needed 22 minutes to reach a successful fault. Here we needed 9 hours. And here we needed only 8 minutes, but even though this percentage is super low. And yeah, this comes back to this variance I told you about before about this number. We just got lucky here, which I mean, that's one of the sexy things about fault injection. You can always just get lucky. Yeah, so quick words about, again, why this is such a cool thing to do. Our typical use case is that we like to bypass secure boot, and this is a really cool way of doing that because you do it before even reaching any authentication or whatsoever. You are you're right in the middle. Yeah, you don't even have to think about the authentication. You just jump directly to whatever you are copying into your device. And another thing is privilege escalation. So most CPUs have some kind of distinction between a privileged and non-privileged mode. In our RISC-V, we call it, it's called user mode and machine mode. So you can imagine that if your CPU is in machine mode and you manage to make it execute code that you control, then you suddenly control the machine mode. Or if you think about REs and Ts, if you manage to get a T to execute your RE code, then suddenly you have control over the T. Yeah, some quick conclusions. We explained to you what is fault injection. We explored various options to use this to control the program counter. We showed that the two cases we thought would be successful before were actually successful. And we also got this unexpected result where we directly controlled the program counter, even though the program counter register is not directly accessible through the instruction set architecture. Yeah, some future work ideas. By the way, if you're interested in this, we are also always looking for more interns. So if you're interested in researching this kind of stuff, please get in touch with us. For example, trying to do this but through jump or branch instructions. And yeah, we did not really talk about countermeasures against this kind of attack or how you could protect this. But yeah, once you would protect it, how could you circumvent those protections is also interesting to look at. So I tried to rush to the end here, so we might still have some time for questions. I'm not sure. It's already 8 o'clock here on my screen, so I think we even ate into your break.
Thank you so much, Niels and Praveen. There was one question asked by Upper. Is there an alternate way to, where is that? Let's say I'm doing it on an actual device. Is there any other way apart from side channel attack in order to extract the instructions where I want to inject the fault? And Praveen has already answered it, that there's no other way. So yeah, thank you so much, Niels and Praveen, for this amazing presentation. Friends, this presentation is recorded and they will be uploaded on our Nullcon YouTube channel. So you can watch them after we do the minor edits of audio and video quality. Yeah, thank you guys so much.
My pleasure.
Thank
you
you
for having us.
Yeah, all right.